Right, continuing from where we were last time. So we had finished this slide, but I will go back again. So we are given 49 megahertz and a cluster size of 7. So each cell gets 7 megahertz. Since it is FDD, half of it goes down, another half goes up. So each really gets 3.5 megahertz uplink or downlink. Now we need 10 kilobits per user, and since we have 1 bits per hertz, 1 BPS per hertz, we need 10 kilohertz per user. Given 3.5, we can support 350 users per cell. And since it requires 100 users per square kilometer, we can cover 3.5 square kilometer per cell from 350 divided by 100. So if it is 3.5 square kilometer cell, the radius would be 1 kilometer, pi r square. Now if you divide into 35 channels and imply TDM, you see 3.5 megahertz, if you divide that into 35, you get 100 megahertz, 100 kilohertz, I think. You get 100 kilohertz per channel, which will give you 100 kilobits per second, using everything same. How many time slots are needed to support the required number of users? Now we need 100 kilobits per user, and each channel is 100 kilobits. So we can put 10 users per channel. So remember, we had 8 slots in GSM. In this network that we are designing here, we have 10 slots. If TDMA frame is 10 millisecond long, how long is each user slot in the frame? Now TDMA frame is 10 millisecond long. We decided that arbitrarily. So now it is 1 millisecond per user then. How many bits are transmitted in each slot? Now each slot will be 1 millisecond times 100 kilobits is 100 bits then. State multiplication. You just have to know where to do what. Anyway, so this is the kind of now calculations that you can do. There is one clear thing in this calculation which I didn't point out, maybe I should point out now, is that you never book a frequency for a user forever, in the sense that users are coming in and out. So if you have one channel, you are going to probably accommodate 10 users maybe there, okay? So you will multiply all these numbers of users by 10, because I think the 10 kilobits here means when the user is active, right? And there will be 9 other users who are not active. They have a cell phone in their pocket but not using it. And so you can support 11 users that way, or 10 users at least that way on that one slot. And so that is called overbooking factor. And that is just like airlines. Airlines actually don't have that big overbooking factors. They have a 10% overbooking. So they book maybe 110 seats, 110 passengers on a 100 seat plane. Here the booking factor, overbooking is very high. So we book 10 times the number of passengers than the number of seats we have. Actually 10 times might be too much, but 3 to 4 times would be good enough. So you got that, right? Everybody got that idea? Overbooking? Alright, so the homework 14C is just a repeat of that example, and you are supposed to do the similar exercise. And then we move on to GPRS. So this is around 1995 time frame. GSM is coming in, but people are complaining about the data, saying that voice is okay, but we need to send some data as well. And GSM obviously gives you only it's 9.6 kilobits per user, which was good for the time, but not good enough, right? So GPRS was introduced, which is General Packet Radio Service. Okay, and now therefore it is 2.5 because it is not 3G and it is not 2G. The GSM has 8 slots per 200 kilohertz channel. So one slot gives you 9.6. With GSM, you change that by using better coding and different coding and channel condition, adapting and all that. You might be able to get from 70 to 170 kilobits using all 8 slots. And how many slots can you use? So you can increase from 9 to 21 per slot. Anyway, 9 kilobits to 21.4 kilobits, and then you can give more than one slot. You don't have to give one slot to the user. You can give more. And in fact, the slot doesn't have to be the same all the time because it is data. So you could give them any number of slots anywhere. Right? Timing is not the key. Synchronization is not the key. For voice, you want to get every, so many millisecond slot because you're speaking. But with data, you could just get whenever you get, wherever you get, you can use it. So then there is this hopping technology which was already there around the time. Hopping means that you give this slot wherever it is empty. So let's say you have these two uplinks, and here this user is not speaking. Whatever was the user here was not speaking, so we give it to GP1, GPRS user 1. Okay, and then this user was not speaking, so we give it to GP1 there, and then wherever. So basically, GPRS is not a fixed slot. It's whatever is available, whenever it is available to whoever wants it. And so that way you get lot more utilization of the link and lot more happier customers because they can do data. Okay, same thing on the downlink. So the G slots are fixed. G is the GSM. GP is the GPRS. All right, so it supports intermittent burst data transfers, and you need to add 2 new elements to the GSM network to do all this data stuff. And those 2 networks are called service for the GPRS node, support node, and the gateway for the GPRS support node. Service is security for the data, mobility, access control, etc., etc. That is the service part. The gateway part is just routing. Okay, and so this is standardized by HC, and now you have 2 more nodes here, 3 more nodes actually. You have the internet, you have the gateway. This is called GGSN, and you will hear it a lot, you will find a lot in the discussions on the cellular networks. GGSN is the gateway, and SGSN is doing the rest of the work that is required for mobility and security and accounting and everything else. And then packet control unit, basically these people don't understand packet that very well, so these are separate functions. And then they tell the controller, okay, give this a slot, what a slot, and all that. Okay. So these are the 3 new functions. This is the old network that we had seen before for GSM, and now we added GPRS by adding SGSN and GGSN. Moving along, obviously, 26 kilobits doesn't do much, so then they went to the next one, which is called Enhanced Data Rate for GSM Evolution, EDGE. Even higher speed. And how do you get higher speed? By having better modulation. By this time, the technology, the wireless people, the signaling people are having better and better coding. So EDGE uses simple 8 PSK. What is 8 PSK? Anybody can guess? PSK. What could P stand for? Phase shift keying, right? Okay. So they just use 8 phase shift keying, and that gives you 3 bits per hertz. Actually, it should be BPS per hertz, not bits. BPS, 3 bits per second per hertz. And so you get 3 times. So with GPRS and EDGE, you get 384 kilobits. Now you're getting there. Right? But the thing is, to get this 8 PSK working, you need really good quality signal. But now we have, if you implement all this, now your RAN, if you remember what RAN was, is now called GE RAN. Why GE RAN? Because it is GSM plus Edge radio network. So this is the RAN, radio access network. Now this will be renamed as, you will put some GSM stuff here, and that will be called GE RAN. Times come for 3G now. We are almost there, 2000. Well, not 2000. This might even be around 2002 or 3. So anyway, and you know how many versions of 3Gs are there? Huh? 3 versions, okay? Time for a quiz next time. So three versions of the 3Gs. Those are American, North American to be exact, European, and Chinese. So basically, we are talking about which version here? European version. WCDMA, European 3G. It is also known as Universal Mobile Telecommunication System, UMTS. That version of 3G. And it uses CDMA, obviously, with 2 megahertz FDD channels, 5 megahertz FDD channels. So 10 megahertz total, and uses direct sequence. And everybody remembers what is direct sequence. There are several methods of CDMA we talked about. There is a direct sequence and there is frequency hopping. So this is direct sequence. And the radio network is now called UMTS Terrestrial Radio Access Network, UTRAN. And the air interface. So now what is the air interface? What is the radio? This is the network, and the interface is right here. You know, the interface between the mobile system and the base station. That radio interface is called UTRA, and the network is called UTRAN. All right. Now, obviously, we could give a whole day lecture on 3G, and there are books on 3Gs, but we really want to move on to 4G, and therefore we are going to move on from 3G right here on this slide. So we are still not at 4G, but basically 3G people are moving forward, and every time they move a step forward, they call it evolution. And this is a strange word, actually. I kind of find it strange that everything they keep evolution. So we saw Edge was an evolution. Now there's an evolution of WCDMA. Okay? And that is called high-speed packet access. By this time, even though there is GPRS and everything else, the things are still being talked in terms of bits and not really in terms of packets. So the keyword here is packet. So they are learning now IP, and they know that, you know, basically packets and all that. So they come up with 2 different technologies. First, they said, okay, let's handle the downlink. Downlink is very easy because downlink is the base station. You can put any complexity you want in the downlink. Uplink is difficult because that is the mobile, and it's difficult to change transmitters in the mobile. You know, it becomes expensive as well. And there are other technical reasons. I can go on about the uplink. So anyway, so they said they first introduced something called high-speed downlink packet access, HSPA. And it used everything that was kind of known by this time. This is now 2005 or 6, something like that, 3 to 6, something like that. So adaptive modulation and coding. What does that mean? That you look at the channel. If it is good, you use higher modulation. If the channel is bad, you use lower modulation. That is adaptive modulation and coding. Channel dependent scheduling. If this person has a good channel, we give them higher. If this person has a bad channel, we give them lower. So channel dependent scheduling. So we schedule them accordingly. Okay, 2 things we could change about them is first when they are scheduled, and what channel they are scheduled, right? And so what frequency they are scheduled. So we could do that channel dependent scheduling, quality dependent. higher order modulation, we already said that. So anyway, with all of this, they could get very high, I mean, not very high, I wouldn't say very high now, given that we are in 2014. So they got higher speeds. Then they handle the uplink, and that is called HSPA, and that basically allowed multiple parallel transmissions. So even though we might have one frequency, a user from this side can transmit and a user from that side can transmit, and the base station will figure it out. So that one is HSPA. And then you combine all of that, and that gives you HSPA. HSPA is just a combination of those two. And now there is evolution of HSPA. So HSPA plus is what we have today. You go to many news items or you go to many services description, they say, well, we give you with HSPA plus, right? So that is just an extension of 3G all the way to 160 megabits down to 22 megabits up using MIMO and multiple carriers. So now by this time, 2014, they know MIMO, I mean, they know MIMO for sure. I mean, I'm saying that they are using MIMO in this track because the thing is, there are parallel things happening which we'll talk about next, which is 4G, where all of this is there anyway. But as 4G people are developing or inventing all of these things, the older people are upgrading their technologies to match, to keep parallel paths, because the new technology requires new equipment. Why not fix the old equipment? So this is fixing the old path, and the next lecture is about inventing the new path. Right? So HSPA plus is the evolution of HSPA, which gives you 168 megabits down, 22 megabits up using MIMO and multiple carriers. Now I haven't defined what well, okay. So let's, for the time being, multiple carrier simply means OFDMA. Okay, but it could mean many different things. So I'm just going to I'm simplifying a little bit here, and really this is not of interest right now because this is really we are moving to 4G, which is what we are going to, where we will define exactly how it is all done. All right. Now with this much, obviously some new words come in, and then you read the literature and you find, oh well, what is this? So we already introduced GERAN. GERAN is GSM plus Edge Radio Access Network. We already introduced UTRAN. UTRAN is UMTS Terrestrial Radio Access Network. And in the next version, when we will talk about next 4G, I mean not actually, again, whatever next we talk about, LTE, long-term evolution. Okay, so this was short-term. Now this is a long-term evolution, LTE. So that is the network, LTE network, and the key technology here was TDMA. Here it was WCDMA. And here it would be OFDMA plus something else actually. So it's difficult for me to say OFDMA here straightforward because this is more complicated than that. But it's not CDMA or TDMA. So anyway, and this was called UTRAN. This is called EUTRAN, evolution of UTRAN. Okay, these are really very high believers in evolution. There can be a problem there, but it is enhanced.
Enhanced UTRAN.
Okay.
Another meaning of.
Okay. Probably I am flowing away maybe.
But evolution is used very often.
LTE is evolution, right? For sure. And all right, so let's see where we are. Okay, on this side, we know what is MSC and Media Gateway. Media Gateway is the one that handles all the multimedia. There is a service gateway which basically talks to this SS7. There is a GGSN and SGSN which we talked about. But on this side here, we have, okay, here it is clearly E for evolved, okay? Evolved Packet Core, EPC. All right? And so this is the packet, this is the circuit switch core, this is the packet switch core, now this is a packet core. There is no circuit, there is no anything else, right? So evolved packet core, and here we have service gateway, multimedia entity, and then we have packet gateway. This packet gateway clearly speaks IP. Okay. Another name change is, this was called BTS, which was basically the base station, base transmitter system, and this is called node B. B has to do with the base, and then this is enhanced node B, not evolved. So this is E and B. Okay, and so right now I'm keeping at this level because, of course, this one is the next lecture, so we will discuss a lot more about this. But this is somewhat past, and you know, given the time we have, we should clearly focus on the future. This is all the words defined. If you don't know the meaning, actually you should know the meaning at least by now. If you don't know the meaning of some of them, please ask me right now. But circuit switch, evolved, packet systems, enhanced gateway support node and all that. Let's see, long-term evolution, serving gateway. Yeah, evolved node B. Oh wow, I was wrong about that E. I was so close to enhanced. I hate to say this, but you see what happens is when the words are invented abroad, they have a meaning which makes sense in the language in which it is invented, right? But when they sound kind of little bit odd here, I mean, I would know. I don't think I would put something as evolved. Let's say there is a enhanced clock. Would I say evolved clock? Right? But in some language it makes something better. Okay. So summary. Okay, summary. In a cluster size of n, a cellular cluster size of n, square root is missing here, but basically the same distance between the cells, same frequency is d is equal to r times square root of 3n. Right? R is the cell radius. D is the distance between the centers of the cell. By the way, on the D upon R is also called, has a name which you need to know. D upon R is called reuse ratio. D upon R is called reuse ratio because, you know, whatever, if suppose radius is 1 kilometer and you are going to use at 7 kilometer, you really extend it by 7, and so this has a name called reuse ratio. D upon R. And so back to this. So D is simply square root of 3n. Then 1G was analog voice with FDMA. If nothing else, this is one thing you know about 1G, that is analog, and that it was FDMA. 2G was digital voice with TDMA. All right. Now here is another thing that is known, is that when we say TDMA, we don't mean that there is no FDMA. FDMA is already there. So we are putting TDMA on the top of it. All right. So this is kind of understood that when I say OFDM, I don't mean that you don't do FDMA. You probably do FDMA anyway, but then on the top of that you do OFDMA as well. So same thing is here, is that TDMA is the key new thing. Most widely implemented 2G is 3 GSM, and data rate was improved by GSM data rate was improved by GPRS and Edge. 3G was voice plus data, and everything is CDMA. All three versions of 3G are CDMA. This is the most widely 3G is WCDMA using two 5 MHz FDD channels. And in a minute it will become clear as to why 5 MHz is the limit. But that was the limit. Data rate was improved later using HSPA and HSPA plus. So these are post 3G technologies. 3.9G to 4G is the high speed data with OFDMA which is coming up. Okay. Reading list. So actually the first book is the most important one. Second one is not. The book GSM to LTE is very easy to read, very new, and covers everything. Now it covers all the way to LTE. So we haven't covered LTE in this lecture yet, but it covers obviously 1G, 2G, 3G. And so I would recommend that you read that. Of course, Wikipedia links and references and everything else.